all of the acids that we have looked at thus far are what we would call monoprotic acids. Um, and that means there's only one proton that they're capable of giving up. So things like HCl and HBr or HNO3, um, these are all monoprotic acids. Okay, and if we're going to have monoprotic acids, well, you can imagine that there's also diprotic acids. Okay, and we've already seen that with sulfuric acid. So that's diprotic. And we can have things like phosphoric acid, which is triprotic. And there's examples of where we would have 4 acidic protons or 5. There's also going to be some acids that look like they have a whole bunch of protons on them, but not all of them are acidic. So for example, if you look at acetic acid, okay, this has the chemical formula C2H4O2. Okay, and looking at that, you might get the impression that this is tetraprotic. It has 4 protons on there. But it turns out that they're not all acidic. Only this one right here is acidic. For a full explanation for why that is, you can take organic chemistry with me next semester. So acetic acid here would still qualify as a monoprotic acid. Even though it has other protons, they're just not acidic. Okay, so let's look at a specific diprotic acid. We'll look at carbonic acid. Okay, carbonic acid is an example of a polyprotic acid. Both of the protons are acidic. Okay, so if I add carbonic acid to water, I can produce hydronium ion plus CO3H minus. Okay, and we can describe that equilibrium with an equilibrium constant that we're going to call Ka1. Okay, but just like we saw with sulfuric acid, that second proton can come off. Again yielding hydronium ion and carbonate. And that can be described with a Ka value as well. We're going to call that Ka2. Now, one generalization that we can make here, and this is going to be true for every acid, is that Ka1 will always be will always be greater than Ka2 and any successive Ka values. That's because every time we pull off a proton from something, it becomes more and more charged, which means it's not so happy. And we can see this here with the carbonic acid, because the carbonic acid, the first pKa, has a value of 4.2 times 10 to the negative 7th, whereas the second one is 4.8 times 10 to the negative 11th. Okay, that's a big jump there. Okay, that's 4 orders of magnitude. So the first one comes off a whole lot easier. Now, let's suppose that we have a 0.100 molar solution of carbonic acid. And we want to know, first of all, what is the pH of the solution? And at equilibrium, what are the concentrations of carbonic acid, the concentration of bicarbonate, and the concentration of carbonate in solution. And as you can imagine, this is just a really big equilibrium problem, which is what we're going to tackle here. Okay, so we're going to start off by looking at the first reaction. Okay, the very first reaction is the dissociation of carbonic acid in water to give hydronium plus bicarbonate. Okay, and we can create an ice table for this. Okay, so we know initially the concentration of carbonic acid is 0.1, and initially we don't have any hydronium or bicarbonate present. Okay, we know some of that carbonic acid is going to react, producing equal amounts of the hydronium and the bicarbonate, so that at equilibrium, the carbonic acid concentration is going to be equal to 0.1 minus X, the concentration of hydronium is going to be equal to X, and the concentration of bicarbonate will be equal to X. Okay, we know that for this process, Ka1 equals 4.2 times 10 to the negative 7th, which is going to equal my equilibrium concentration of hydronium times the concentration of bicarbonate divided by the concentration of carbonic acid. Okay, so we get 4.2 times 10 to the negative 7th equal to X times X divided by 0.1 minus X. Okay, so then we get 4.2 times 10 to the negative 8th minus 4.2 times 10 to the negative 7th X is equal to X squared. We put this into quadratic form. And set that equal to 0. Now all we have to do is plug this into a quadratic formula calculator. Okay, and we wind up with two values for X. We're going to take the positive one because that's the only one that would make sense here. Oops, 204.7. Okay, so that's going to be molarity, so that we can say then that the pH is going to equal the negative log of the concentration of hydronium. Okay, and if the value of X is 0.000247 molar, that must be the concentration of hydronium. So the pH then equals the negative log of that value. And I get a pH equal to 3.69. Now, what about the other stage here? Well, we're not quite done yet. We need to take the bicarbonate and show that undergoing dissociation as well. Giving us carbonate. And again, we're going to create an ice table, but notice there's going to be something a little bit different about this ice table. Our initial concentration of bicarbonate here is going to have to come from here, okay, that value for X. Okay, so that's going to be 0.0002047. Not a very pleasant number to work with, but that's fine. Okay, and the hydronium concentration is also not going to be 0. The hydronium concentration is the same value. The carbonate value, however, is going to be equal to 0. And because that's 0, we know that we're going to shift to the right here, so we're going to lose reactants and form product. Okay, we know that Ka2 was equal to 4.8 times 10 to the negative 11th. Okay, which is going to be equal to our equilibrium concentration of hydronium, which is, I'm going to switch this over to scientific notation here. Okay, there we go. So we plug those values in, and now we just need to solve for x. Now this isn't quite as straightforward as the others, but it's still doable. Okay, so we get 1 times 10 to the negative 14th minus 4.8 times 10 to the negative 11th x is equal to 2.0 times 10 to the negative 4th x plus x squared. And we can simplify this down into quadratic form. Okay, so we wind up with x squared. And then for the second term, we can see here that the 4.8 times 10 to the negative 11th is way smaller than the 2 times 10 to the negative 4th. So we're not even going to worry about doing the math on that. We're still going to come out with 2.0 times 10 to the negative 4x. And then subtract from that 1 times 10 to the negative 14th, and then, as we did before, set this equal to 0 and plug it into our quadratic formula calculator. Okay, again, we get two different values for x. We take the one that's positive here, and we get 5.0 times 10 to the negative 11th. Okay, and that's going to be equal to x. I'm sorry, not equal to x. If that's x, that means that is going to also equal our concentration of carbonate. Okay, now what's interesting here is if this is our concentration of carbonate, okay, and we see this number, it's going to be 5 times 10 to the negative 11th, and compare that to these starting concentrations, we see that as such a tiny number. If we wanted to, we can go through and we could try to do the calculation, but it's pointless. The 5 times 10 to the negative 11th is just an insignificant value compared to the others. Okay, so that means that at the end of this equilibrium, the concentration of HCO3 minus is going to be equal to 2 times 10 to the negative 4th molar, actually 2.0. Okay, the concentration of hydronium will be 2.0 times 10 to the negative 4th molar. Okay, so these are our equilibrium concentrations for all species that would be present. We also have to take into account the concentration of carbonic acid. We didn't do the math on that earlier, but that's going to be equal to 0.1 minus x, which was the 2 times 10 to the negative 4th. Which, unsurprisingly, works out to be roughly 0.1 molar. Okay, notice the pH that we calculated was based on the same value for the hydronium concentration that we wound up at the end. What this means is that the first deprotonation, the first ionization, is the biggest contributor to the pH of the solution. Anything after that is going to be minuscule. Okay, so that is how we deal with a polyprotic equilibrium.